This video covers the exact diagonalization of the Heisenberg spin chain, a computational workflow for modeling quantum mechanical systems. We consider a one-dimensional Heisenberg spin half chain with n sites and periodic boundary conditions defined by this Hamiltonian. Our goal is to construct the Hamiltonian matrix, compute energy eigenvalues and eigenvectors, calculate thermodynamic properties, and plot the specific heat and magnetic susceptibility. The physical system is defined as a ring of spin half sites with n number of sites, with the Hamiltonian defined by J, the exchange coupling constant, and SI, the spin operators at site I. Periodic boundary conditions are applied. The computational workflow involves 4 phases. First, constructing the Hamiltonian matrix. Second, computing energy eigenvalues and eigenvectors. Third, calculating thermodynamic properties. And finally, plotting specific heat and magnetic susceptibility. Phase 1 is about constructing the basis of spin configurations. The system must be built using the SZ basis, mapping every possible arrangement of up and down spins to create the full state space for the Hamiltonian. To efficiently construct the matrix, we generate the SZ product basis, mapping every configuration to a matrix index via a state-to-index lookup table. This saves computational effort when the Hamiltonian flips spins. Deconstructing the Heisenberg interaction reveals a diagonal part, representing the Ising-like energy, and an off-diagonal part, which is the quantum spin exchange that mixes the basis states. Calculating diagonal contributions involves multiplying the SZ values for neighboring sites. For parallel spins, the contribution is plus 0.25J, and for anti-parallel spins, it's minus 0.25J, yielding the pure Ising diagonal energy when summed. The off-diagonal part involves the quantum flip-flop, where neighboring anti-parallel spins are flipped. The modulo operator ensures the periodic boundary conditions, connecting the last site back to the first. For n equals 8, the Hilbert space contains 2 to the power of 8, or 256 basis states, which results in a manageable 256 by 256 matrix. The product basis and state-to-index map are crucial for fast lookups. The Heisenberg interaction is broken down for code implementation. The diagonal part involves a 0.25 factor correction. The off-diagonal part is the flip-flop term, which adds J/2 to the connecting matrix element. Constructing the matrix involves 2 elegant fixes: using the modulo operator to achieve periodic boundary conditions, and applying an equation to ensure perfect Hermitian symmetry, eliminating floating point errors. The numerical matrix construction maps the Hamiltonian operators to a banded matrix, which includes diagonal and off-diagonal elements, with the constraint of periodic boundary conditions. Solving the quantum system is achieved with a single line of code, using NumPy's linear algebra function to compute the exact energy levels and exact many-body eigenstates. This completes the exact diagonalization. A crucial correction is computing eigenstate magnetization. Magnetization is calculated using the squared amplitudes of the exact eigenvectors. This conceptual upgrade ensures susceptibility is derived from macroscopic properties. Numerical stability is achieved by taming the Boltzmann weights. We subtract the ground state energy, E0, before exponentiating. This shift prevents exponential underflow at low temperatures, avoiding absurdly tiny weights. The partition function, Z, is the master quantity that unlocks all macroscopic properties, calculated as the sum of Boltzmann weights. The average internal energy, U, is a simple Boltzmann-weighted average of the exact eigenvalues. We compute the specific heat, CV, derived from energy fluctuations, and the susceptibility, Chi, derived from pre-computed magnetization values. The temperature grid starts at T equals 0.1 to avoid division by 0 errors in the formulas. Visualizing the thermal response shows distinct peaks for both the specific heat and magnetic susceptibility. These peaks indicate the temperature range where energy levels contribute appreciably to thermal excitation in the finite n equals 8 system. The full machine progresses from microscopic spin interactions to the exact spectrum via diagonalization, and finally to the thermal response using Boltzmann sums and thermodynamics. This turns a quantum problem into finite linear algebra.